and I will remember to record this time. So we've seen that we take a program and we describe conceptually how you parallelize the I/O in MPI/IO, and we ran a simple benchmark. But you saw that there was, by simple changes to the lustre file system, just changing the number of stripes, we're able to increase the I/O by an order of rate by an order of magnitude. So this lecture is sort of talking a bit more about how you make efficient use of the lustre file system. So said, the important point is where are the bottlenecks? And we said there can be, they can come at a lot of different places. We saw that for actually a single process was really bottlenecked at sort of 0.5 gigabyte a second. So you could try multiple processes, but we saw that on a node you could get up to maybe about 12. So there was that was maybe we wouldn't call it a bottleneck. It's a limit of about say 10 or 12 gigabytes per second from a node, and then you might increase the number of nodes to get that. So that there can be bottlenecks in getting the data out of the processes onto the network. But then there can be bottlenecks down here. If we do a large number of small files, you can see bottlenecks on the metadata server. Now you have to use, luckily on ARCHER2, you have to use really quite a large number of files, into the many thousands, but you do see it. And then there can be bottlenecks in basically accessing. You might saturate the bandwidth of a single OST. That might be the bottleneck, in which case you want to use multiple OSTs. There's lots of places where you can get bottlenecks. And I think it's really important, and people do tend to forget this, that the performance of any thing, but a particular computer system is limited by the slowest part. So, for example, if you go and play around with writing to the NVMe, the solid state disk on the /scratch file system, on paper, the bandwidth is much higher than the spinning disk OSTs, and there are more of them. However, there's no point in using that if your bottleneck is, if your bottleneck is getting the data off the process. It doesn't matter. Okay, so it is important to understand what the bottlenecks might be. So caution, as I said, I/O benchmark is very difficult and can be non-reproducible. You're sharing the ARCHER2 system with other users. Someone else may be writing to the same OSTs. Someone else may be using the same network links. And so, you don't often see this in message passing programs unless you're doing very large. If you're just in computation, you would only see this using very large collective operations with a large amount of data, such as the kind of global transpose you need to do in large Fourier transforms, for example. That's where you tend to see it. But you may, to be honest, the typical reason why you see contention, why you see poor I/O performance, is somebody is writing a lot of data to the same OST as you, or somebody is doing a lot of traffic on the MDS, and that is everything has to be serialized here. So because the MDS has to maintain a consistent view of the file system, it only deals with requests one at a time. If it's overloaded with somebody creating 10,000 files, then you're going to have to sit and wait. So often the MDS is the point of contention. So caching can also give very high I/O rates, especially with small files. I find this most difficult for some reason with reading. That basically, if you read data, then you read it again, it will be cached somewhere in memory, often maybe on the node. So Linux has a habit, so like a good habit basically, of any unused memory at any time is often used as a disk cache. So if you've got a 256 gigabyte node and you're only using 128 gigabytes, then it will cache disk data in there. And so if you read data more than once, the second read is really good. Now, as a user, that's fantastic. It means you get really fast speeds. Of course, if you're trying to benchmark, it becomes quite difficult. So if you're trying to do benchmarking of read, what you tend to have to do is to write on one set of nodes and make sure you read back on a different set, for example. The other thing is ensure benchmarks run for a reasonable amount of time, a few seconds at least. and repeat them several times to do that. So that's, again, you know, you're never going to get it. There's no such thing as the perfect answer, but typically what you get when you try and do IO benchmark, you get similar results for a long time, and then you get a peak and it's really slow, just like if you drive to work. Okay, nine times out of 10 over a fortnight, you get in about an hour, so 45 minutes. One day there's an accident, it takes you 3 hours. So you tend to get fairly reproducible numbers and then occasional outliers. So I've talked about the ARCHER2 hardware. I've said it's now 4 separate work systems. I can't remember where the 4th one came from. I think it was inherited from somewhere else. I can't remember. But each has 12 OSTs and 1 MDS. As I said, the consortia are assigned. I had this slide before, different partitions to share the load. And we have these SSDs, not spinning disks. And in fact, it might be worth, while we're here, just looking at what the hardware specs are, because we didn't really talk about this, but I did summarize them. If I maybe share, there's a paper linked from the website which we did a while back. Let's just have a look at that just to get these. So this was the Cray user group back in 2022, which was held in California, in Monterey. It was going to be a great trip for me, and then I got COVID 3 days before I went, so I had to present this remotely. So all my California trips were cancelled. But I summarized somewhere in here the hardware specs. I thought. Okay, table 1, sorry. Okay, so I just have the capacity here. So I remember that I think that the NVMe has, each of them has a bandwidth in principle of about 50 gigabytes per second, and there's 20 of them. So that should be something like a terabyte a second. Whereas the OSTs for ARCHER2, as I said, there's 12 of them, and there's about maybe 10 gigabytes per second. So in principle, the storage speed, although they're smaller in capacity, the storage speed of the NVMe is an order of magnitude faster than the spinning disk, a factor of about 5 from the actual hardware, and then a factor of 2 because we have twice as many of them. I thought that we quoted these. Apologies. I should have. Yeah, there we go. So these are the stated peak bandwidths of the two. Sorry, they weren't on the table. The stated peak bandwidth of the OSTs are 11 gigabytes per second, 55 gigabytes per second for the spinning disk, and the NVMe. So that's useful figures. So apologies, it took me a while to find that. I'll go back and share the actual. And this is talking about the work file systems having about 3.3 petabytes storage each. So if you're doing serial I/O, so you're not using any parallel libraries, there are 2 ways you could be doing this. You could be doing a single file with controller I/O, a single writer. So that's the controller I/O. You write some MPI to collect all the data and funnel all the I/O through a single serial process, let's say rank 0. Or you could have file per process, many independent writers. Both of those are fundamentally, the library calls you're doing are serial library calls, fopen, fwrite, fclose. However, in one case you're only doing one, and in another case you're doing lots of them at the same time. For both of these, there's little point in striping the file. Okay? For a single file, the performance bottlenecks appear to be elsewhere. It appears to be a single process can't write more than about 0.5 gigabyte per second, And so there really is no point in striping the file. I mean, the bottleneck is you're not going to improve that. When you write multiple files, you're using parallelism because each file is going to a different disk, a different OST. So by striping, you're kind of complicating things. And it's actually, there's no point, okay? Because if you're writing more than a few tens of files, and there are a few tens of OSTs, you're parallelizing across the OSTs by having many I/O. So this is why single stripe is the default, because a lot of people do this. But my ballpark here, single can achieve about 1 gigabyte per second. That seems a bit optimistic now. We're getting more like half. I need to investigate why that figure seems to have gone down. It may have been throttled to try and eliminate bottlenecks elsewhere. I need to find out. But for serial I/O, whether you're doing a single controller process or serial in the sense of each I/O request is serial, operation is serial, but you've got lots of them, i.e. file per process, then there's no point striping the file. The MDS can become overloaded. Opening and closing a file requires MDS access, and this is therefore a serial operation. Well, you might say, well, I just open a file at the start, don't I? Well, first of all, this is a very, very user unfriendly thing to do, because if you do this, you're blocking other people out. But one of the real patterns we see, which is a complete nightmare, is people. I can see that this is a way of writing elegant modularized code, but whenever you write results, you open, seek, write, and close operations. That is just a total disaster. Okay. And there are some applications, there's an engineering application called OpenFOAM that in the past has done this and just brings the whole system to its knees. So tricks, don't try not to write too many files. Once you've got a file open, you've paid the cost of opening it. Keep it open. Don't keep closing and reopening it. But actually a simple trick is to have a file per node rather than a file per process. So you want to reduce the number of files. So there's not really much point in having more than a few hundred files. So remember, for the disk system, the total bandwidth of the disk system is maybe 100 gigabytes per second. You're getting about half a gigabyte per second per file. There's not much point in having more than a few hundred files. Whereas if you're running, say, you could easily run on many, many thousands of processes. So the simplest next quantum down is don't write one file, that's too few. Don't write a file per process, that's too many. Write a file per node. Remember, that's a natural thing to do, because each node is a client of the file system, and also collecting data on a node doesn't require using the network. So you're not so it's basically just memory copies. So that is quite a useful thing to do. If you are going to write multiple files, having a file per node is much better than a file per process. It cuts down the number of files by 2 orders of magnitude, by a factor of 128. If you must have lots of files, consider multiple directories. Every time you look for a file and try and open a file, the file system has to open the directory, say what files are here, and search through them in order. So maybe a directory. So if you must have a file per process, maybe have a directory per node, for example. But I think file per node is a nice halfway house where you'll have a few hundred files, but many, many fewer files than if you did file per process. But if we are doing parallel I/O and we want to benefit from striping, so we are writing to a single file and it's striped across different processes, different OSTs, you can vary the stripe size. The default of 1 megabyte seems quite small, actually, because if you're writing gigabytes of files, that's thousands of stripes. Apologies. So if you're writing anything more than a gigabyte, the stripe count will be in the thousands. We only have 10 OSTs. That seems to be rather too many. It seems, at least to first approximation, seems like rather a small granularity. You can basically experiment with larger settings. I have to say, though, I have never found much benefit from this. I found that in practice, the stripe size, the default stripe size of 1 megabyte is actually relatively useful. I haven't seen a huge amount of performance benefit from it increasing the stripe size. Don't set it too large, of course, because if you set it too large, you won't be using all the OSTs. So remember, if you have a huge stripe size, the file will only be divided into a very, very small number of sections, and then you won't use all the OSTs. But in my experience, I have not seen any performance improvement from significant performance improvement from playing around with the stripe size. So how does parallel I/O work? Well, how did, when you called the MPI I/O functions in the last run of the benchmark, it went 10 times faster on 12 stripes, at least with 12 nodes. How did that do that? Well, MPI I/O auto-configures to the luster settings. That's why it actually works quite well. That the parallel I/O libraries on ARCHER2 are aware of luster. They're luster aware. So what I talked about the fact that you want to you want to aggregate data. So you want to basically collect data together so that a large number of fairly small write operations or read operations become aggregated into a large number of small operations. You don't want too many people writing data. You don't want too few. So what MPIO does is internally it identifies a small number of what it calls aggregator processes. So it nominates a subset of your ranks to be aggregators, and hopefully they're spread across nodes as well. Because remember, each node has a separate network link, so you want to utilize those network links. What it does internally, at least sort of my naive understanding, is it uses MPI collectives, and this is good old-fashioned MPI, such as scatter or gather, to aggregate data to these processes. So basically, now remember the network bandwidth of ARCHER2 is way, way faster than the I/O bandwidth to disk. So it's worth reorganizing data and paying that slight cost before you write it. So what it does is you nominate a subset of nodes as of processes as aggregator nodes. They then gather data from whoever they're responsible for, and then they write it out. And so you then perform a small number of large write operations, and it minimizes the overheads of locking, such like. Now, this is, of course, only possible with collective I/O calls. So you have to call the _all version. And it can be quite hard to work out what's going on. And actually, there is a nice variable you can set called export MPI-ch MPI-IO stats equals 1, which will give you a breakdown of what happened. So what it will say is, you wrote a gigabyte of data, and this required, 1,000 writes of a megabyte or 1 write of a gigabyte. You will get very quickly information on whether or not your data was aggregated well together. And so that is a very useful thing to set, and it gives you quite nice output. So that's a very useful debugging tip. And also, this may work for libraries like HDF5, which where you don't call MPI-IO, but maybe they do under the hood. So this can even be useful to analyze the I/O characteristics of other libraries like HDF5 and NetCDF. Because if they're calling MPI-IO under the hood, then this will trigger the logging in MPI-IO, which is useful. So, what happens here is that what we would like to do is to have an aggregator process for each disk or each OST. And that's because if we have multiple, if we know that there's only ever one process writing to each OST, then there's no locking issues. Okay, so if you can arrange for there to be a single aggregator process per OST, then you can do things like, well, okay, I'm responsible for OST2. I've called it disk 2 here. I am going to take that data together. I'll collect that from whoever owns it, then write it out. Okay, and so that allows you to, if you assign an aggregator per OST, then you can then collect data appropriate to that OST and guarantee that when you write it out there, that there's no locking required. And in fact, that's what MPI-IO does. It allocates one aggregator per stripe. So this is nice and it's not nice. It's nice because, and that's why we didn't get when we ran with you have to run on a large number of nodes to be able to get this benefit. But what MPIO does is by default it uses one aggregator per stripe. That seems like a nice thing to do, except unfortunately we've seen that the I/O for a single process is only about 0.5 gigabyte per second, and that's why we were capped at 5 or so gigabytes per second on 12 stripes. So you can change this. And you can say export MPI. This is a horrible syntax, but this says for all files, allocate 4 times as many nodes, aggregator nodes as you previously thought of. However, so this causes multiple processes to write to the same OST, and for reasons I don't quite understand, it uses a default locking approach, which is incredibly inefficient. And so what you can try and do is to use this very, very bizarre syntax here, where you say for all the files, use the lock mode 2, which is an efficient lock. Why it doesn't use it by default, I have no idea. But anyway, it's an efficient lock mode, and you use 4 times as many nodes to do the aggregate. So you can attempt to. It'll be worth trying to see. Now the I/O behavior of the system has changed slightly over the past 6 months because we had this big software update. 3 or 4 months ago. So a lot of things have changed in the system software, but the hope is that this will increase the I/O speeds. Again, it's no work for you, it's just a configuration step. For all these things, you have to be using collective I/O. You can also switch MPI versions because for some I/O patterns, it's actually that data aggregation which can be a bottleneck. You would hope not, but it can be. So for the default network layer, I don't think you need to do this anymore, but at least in the early days of ARCHER2, you needed to set this. So this is basically, they're saying that I/O comprises 2 phases. One is aggregating the data together onto the aggregator nodes, which is MPI operations internal to the machine over the slingshot network, and then writing the data out to disk. And there are 2, at the very lowest level on ARCHER2, there are actually 2 protocols for transferring data over the network. The default is called OFI, Open Fabrics Interface, but you can switch to something called UCX, which is the Mellanox layer. And for large collectives with heavy comms load, it does seem to be better. The nice thing about this is you don't need to recompile. In your Slurm script, you just do module swap this. You may need to do a module load lib fabric, which is in the sheet, but basically you don't need to recompile. So again, you can test this just very quickly and see whether it helps. It's a freebie, basically. Common mistakes. The common serial I/O mistakes, the text data files. Don't write text data files. I mean, they bloat things. That part is just a huge amount of processing just to write out numbers. Write raw data. The amount of data will be smaller. There's no parsing required on input or output. Multiple accesses to a large number of small files, that's a classic thing that people do, and that can, that's what I said. This, I mean, OpenFOAM, and it's in try not to be too critical, but in one of its modes, it can write a file. It's an engineering time-stepping finite element code. It can write a file for every process, for every different variable, for every time step. So you can end up with hundreds of thousands of files. It really is, very, very challenging. And if each one of those is accessed with an open seek write close, then it's really, really not possible to sustain any reasonable I/O speed. Otherwise, using striping for serial I/O, there really isn't any need to. If you're doing serial I/O, by serial I/O, I mean you're not calling a parallel library. So you've either got controller I/O or you're writing multiple files by using multiple F opens from different processes or nodes. There's not really any point in striping. The other point, parallel I/O mistakes, using a parallel I/O library but not striping the file. I mean, my favorite queries ever have been, I've gone away and spent the last month putting parallel I/O in my MPI code. It doesn't go any faster, and I just say LFS set stripe -C-1, and their code goes 10 times faster. That's always quite nice to do. The other mistake is putting in parallel I/O but not using non-collective individual I/O to a single file. The other problem we have is people contact the help desk, my IO is slow, and you say, how long does it take? An hour or 5 minutes. That's not really any useful information. It's like someone saying, my commute to work is slow. How long does it take you? An hour. Well, if you're traveling across London, the underground, that's quite good. If you live 100 meters from where you work, that's bad. You need to quantify these things in gigabytes per second. Okay, gigabytes, the only rational metric is how big is my data set, how long does it take to write out, how fast is it in terms of gigabytes per second. And you should be able to achieve in excess of 10 gigabytes per second for parallel write, although the numbers seem to have dropped slightly since the last software update. But maybe our magic CB lock nodes multiplier will help us there. But so again, some people sometimes complain about their IO. You're getting really fast performance. It's just you got a lot of IO to do. Maybe you can try and reduce the frequency you do IO and such like. So conclusions for parallel IO to a single shared file, use a high-level parallel library. I've talked about MPIO here, but I will in the final lecture talk about, at least outline how the other libraries work. Use collective calls, stripe file across all OSs. I've never seen a benefit of an intermediate stripe count. I mean, it's useful to do scaling studies and try and understand what's going on, but in practice, either one stripe or all the stripes. That's what I found. For serial IO, single or multiple files, do not stripe the files, e.g. except the default on ARCHER2, and consider writing a file per node. As I said, the controller IO only uses a single disk. File per process may overload the MDS, but consider file per node or multiple files per node to utilize the full bandwidth. So it's nice to have some slider to say, I'm running on 4,000 processes. I'm not going to write one file or 4,000. I can slide up and down to write something in between and find what your sweet spot is. So that's basically, that was a relatively short talk. The exercise, I have to take questions, but the exercise is, apologies, I seem to have lost the, okay. There we go, it's up there. So we saw that sorry, we're here, aren't we? Yeah, we saw that you could get up to about 4 or 5 gigabytes per second on 12 nodes, but there are a number of things we can do. We could look at the stats, we could change the stripe size, we could change the MPIO library. I have to say, this is probably the one that I would recommend trying first. This rather strange syntax here is the one which I think is liable to have the biggest effect. You might want to use more. So what you want to do is to run this with the default of multiplier of 1 and then do 1, 2, 4, 8 and see if it helps things. And I said I haven't had a chance to do this study since the upgrade, so I couldn't actually tell you what the answer is going to be. It used to be MPICH, MPIO stats. Give me a second. That's strange. Give me a second. So I'll stop. Okay, so this has always worked in the past, unless there has been quite a significant update to the. So I don't quite. So Mark, what are you saying there? Have I got a type? It can sometimes be a font issue in the PDF that can cause problems. No, it should. You should be able to do that. Let's just try it. Let's see. So if I'll share my. So you should be able to see my. I'll just check that there is some. Okay, so there's nothing running at the moment. Yes, yeah. So that should work. I don't. Yeah. So it does. It does. I'm sure it does work. And there can be weird font issues if you cut and paste things from from PDF documents. So who is having the problem? So I've slightly lost my thread here. So Oakley was getting some issues. Is it a slide? Apologies. So have I got a problem in the slides? Okay. So I need to fix that. Apologies for that. Are you saying that? That's weird. I think the slides are, sorry, my slides are the same as the, have I got versioning? You're in the hints. Oh, sorry, the hints. The hints. Apologies. Okay. Right. Sorry. So the hints. Yeah, the hints. This is very weird. It is a very weird. I've got a semicolon separator here, and you're saying that in the PDF, I have a comma. That is correct. So that is a good question. They may both be valid, but I'm not entirely sure. So let's have a look. What was the syntax again? It's got a comma separated list here, which is I think what I've got in the I'm pretty sure that the exercise sheet is correct. You can cut and paste from the exercise sheet, but there may be an error in the slides which have not been. Okay, so that's a transcription error in the slides. Give me a second. Yeah, I think you're right. I think that should be a. Yeah, so I believe the exercise sheet is correct because that's the one which people cut and paste from. But I think that you're correct in the slides. It's not quite right. Okay, so if you were to do the multiplier thing, keep the lock mode equals 2. That's a statement that we want to use the sufficient locking mode. No idea why it doesn't use it by default. But the CB nodes multiplier, 1 is the default, but 1, 2, 4, 8 might get you some benefit. So that would be definitely worth trying. So there's a few things to try around, and I said I apologize. I haven't actually rerun all these exercises since the summer when the system went through an upgrade. We're interested to know what the results are, but we're basically just having what we'll do is have a see what results people get for these. So I would say that, in that final session, I'm more than happy from half 3 till 4 to answer people's questions about their own codes and such like. But that's what I propose is we work on the exercise until 3 p.m. A short round of the results. As I said, I have reference results, but they're from before the summer, so I don't know how what I'm looking for, but before September. I don't know how representative they are. It'll be useful to see what we get now, and then finish off exercises and things. I think it's important to note, though, that almost all these changes are external to your program. You're not having to recompile the program. So that is quite nice. If you use fairly basic vanilla default IO in your, using a parallel IO library in your code, then you can then do a lot of configuration and optimization outside of that through magic environment variables and settings and such like. So that's a nice thing to be able to do. I will stop the recording and I'll keep the recording going. So okay, I'm back from that break. Well, did anyone get any? Yeah. So, well, actually, I think you should be able to share the screen. You're welcome to share the screen. Yeah, if you don't mind, it's being recorded. If you're happy to, that's great. Yeah, you should be able to. If I'll stop sharing. Maybe I need to give me a second. It's Oakley. Give me a second. So I may have to give you permission. Make presenter. Okay, so you should now. I think it was Oakley who said they wanted to. So you should be able to, Oakley, now see. Mark, sorry, wrong one. Sorry, it was Oakley and Headley that that confused me. So it's Mark Headley, number 2, I think here. Make presenter. So you should see a little, if you an icon at the bottom with a share content. Can you see that, Mark? And then you should be able to share. Okay. Good. We're seeing it now. Okay. Excellent. So, so my experience. You can do audio if you want, Mark. My experience is that with this multiplier, the IO speed can be quicker, but it's more variable. But this doesn't look. Oh, so you're doing. That's all NetCDF. Okay. Maybe you're interested in NetCDF. So.
Hi, David. Can you hear me okay?
Yeah, I can. Yeah. So.
Did that not work?
No, I think it works.
I can hear you. Oh, what's going on here? Can you hear me? That's my...
Can you hear me now, David? Sorry, we're in a shared room, so we're playing with the audio setup.
Yeah.
Okay, great. So yeah, as you noted, I'm doing this with the NetCDF piece just because that's the one of most interest to me at the moment.
Yeah.
I seem to be seeing quite a significant boost from doing this Cray CB compared to not doing the Cray CB settings.
Okay.
I think
you probably want to run on 8 or 12 nodes to get to see, because a low number of nodes is not always representative. But it could be. Give me a second.
I've got this.
If we go to.
I think I left them running. Just let me check. Yeah, there you go. That's the numbers on 8 nodes.
Okay, this is interesting. Okay, fine. There's still disappointing in this. So which of these? What are we varying here? So can you?
So we're doing striped and full striped.
Okay.
2 runs of each one, and they're all an 8 node 128 by 128.
And what were the settings for the CB whatever? Oh, there's a CB and there's a no CB. Okay.
So the
okay, I see it at the top. Apologies. Yeah, I've got them. Sorry, I was not parsing you. No, I've got it. I can see now in the output. Yeah. So the top. Okay. So for example, the best you got at the top, and they're still similar, aren't they? You got 2.66 at the top and 2.7. It's not a huge difference.
No.
Yeah, it's fun, these things that was the magic. The magic. So net CDF. I'm surprised it's not the net CDF. Well, I'll come back to this. Net CDF, there's quite a lot of hierarchy there. I'll come back to that. But I am. It's going 10 times faster, but it's still only 3 gigabytes per second, which isn't brilliant. So it looks like the CB node thing isn't making a huge difference, basically.
That was my observation too. Yeah.
Yeah. No, that's interesting.
Of a difference when I was running on the 4 node, but I'm not confident enough of the results to be able to say it definitely is. So, do you think it's possible something's been updated on your platform that means this is doing something more sensible than it was by default previously, or something?
It's either doing something more sensible by default, or no, I don't think it is, because basically you would expect to get a multiplier. So if you get by default you have one aggregator per node, yeah, and we've seen it can't write much more than 500 megabytes a second, half a gigabyte per second, and that's way under the bandwidth that the nodes can sustain. So you'd expect that multiplying the number of aggregators would give you, multiply that up, and you would get, maybe twice for small. And it's not happening. So the problem about all things relying on environment variables is that if I've done any kind of typo or something, did you have MPI CHIO stats turned on?
MPI.
A hint. Sorry, stats. Yes. So can I actually see the output? Because in the output it will actually say how many aggregators there are. Well, so I may have made a typo or something, in which case, the problem about environment variables, you set random environment variable at random value. There's never a syntax error. It just said, so it's worth. That's why it's worth checking. But this is something I will follow up if this isn't working anymore. I think it's at the bottom. Is it at the bottom? Oh, here we are. Yeah. Aggregators equals 4. And how many nodes was this?
So this is running on 8 nodes.
That's weird. That's unstriped. Sorry. Okay. So that is good. Go to the bottom. Sorry. It's multiplied out by a factor of 4. So 48. So it is working. Okay. So you were getting, yes, it's aggregators. You were getting the multiplier. And we were not getting a huge benefit. So that is something. And you were doing this lock mode equals 2 as well, weren't you? As we
I believe so. I believe.
Yes. Because that is. I think this has changed since the September upgrade. I mean, it is now a different operating system under the hood. It is a different version of Linux, I believe. So that could have quite profound effects on I/O. So that's okay. So I mean, that's unfortunate. There may be other magic incantations now, but I will follow that up. Okay.
If there was a subtly different way of setting this that would have a different effect, that'd be quite an interesting thing for you to feed back to us after the course. If it was yes, the effect is there, but you have to get access to it differently, that'd be quite helpful to know.
No, I mean, because what's weird is having no effect at all. So it's increasing the number of aggregators. If the lock mode was wrong, it would just the I/O would plummet because they would all be contending with each other. But it's not. So clearly, it's not doing something. It's doing something sensible-ish, but it's not making any difference. I don't understand. I have to say.
Yeah, we tried to do this side-by-side look to see if we could see. And I know I'm just graphing in here, so it's a little bit hard to parse.
No, but you're getting 2.6. It's the same. You'd expect it to be at least from going from 1. From the multiplier equals 1 to the multiplier equals 2, you'd expect it to go up by a factor of 2. That would be your, that would be your guess, and it's not. So that is interesting. That's changed since the last few months. Okay, Okay, that was it. So that is, that's interesting. I think it is important to have the IO stats on, so you can double check that it is, and that was doing what you expected. Okay, thanks. Okay, so I'm sure that hasn't worked. We will look into that. That's news to me. Okay, so I want to. There's one. I'll just.
Thank you.
I'll make you back to a participant again. So there was one. I add an extra slide. I will upload these. Aren't uploaded yet, but I will upload them to say that I sort of said that there was that you should. Apologies. A nice thing to do was to reduce the number of files, so have one file per node. That can be a bit difficult to do sometimes. So an intermediate thing is imagine you have a code which normally just does. Which normally does this. It just writes file from this process. Okay. So I think we've got. I've maybe messed up the sharing. Somebody is. Ed, can you mute yourself? Just. I'll mute you anyway. Fine. Okay. So imagine you have a code which just does the naive thing, which is it writes one. It does this. It writes file from this process. Okay. And it's hard for you to reduce that number of files. Another thing you can do is to make sure that at least on a node, then only written out one at a time. So the problem with this is if I run on 8 nodes, so if I run on 100 nodes, I have 12,800 files being written to at the same time. Yeah. So what we can at least do is there's very little benefit in having, we can basically throttle that and say, look, on each node, if we're running on a large number of nodes, on each node, let's make sure that at least the processes, the ranks on a node take it in turn. And it's quite simple to do that. This came from a query which I did. So what you have to do is you have to create a communicator per node. So there's a nice routine called MPI com split type, which says basically this syntax basically gives you a node com. This splits MPI com world, so every processes on the same node end up in the same communicator. So having done that, you can basically say, okay, I'll find out what my rank on the node is, and I'll find out what the node size is, and then basically I'll loop over all the ranks. So me and everybody on a node is doing this loop together, but to make sure that they do it one at a time, you only everyone does the loop, but you only do the IO when it's your turn. And the important thing is the barrier. Okay, without this barrier, you've done nothing. But what you're doing is saying on the first loop, rank 0 does it, then they all wait. On the second loop, rank 1 does it, then rank 2, then rank 3. And we have seen this converting a code which brought the file system to its knees to one that didn't bring the file system to its knees. And also the IO went up by about a factor of 4 or 5 because they were running on like thousands of nodes and they were just flooding the network. So this just throttling back. When you're on hundreds of nodes, you want to throttle back because you're in the regimes of contention. It'd be nice to have a single file per node, but if you can't, you can at least make sure that all the processes on a node write in order. And this is a little bit of code which does that. I will tidy this up, but this came from a real query I did for a user. So the final thing, and hopefully maybe touch on some of the things that Mark showed there, is other IO libraries. And this is really quite brief, but it's really to basically let's check I am recording, which I am. So I'm surprised this again is I'll talk about how that I'll talk about that here. Give me a second. Again, a lot of these results are new as of September, so that's why I'm being slightly caught on the hop from this because I wasn't able to. So, right, you can see all that stuff now. So I'm going to talk about some of the issues with MPIO and a very brief overview. And I'm far from an expert on these things, but what I know about HDF5 NetCDF, and I'll talk about ADIOS too. So the issue with MPI is that MPI is not a file format. MPI-IO is just a way to write data to file. And so by default, there will be no header information. You're just writing raw bytes. So for example, you get the issues that the storage is architecture specific. Your big little endian will just be reflected in that. And so for example, I do a weather forecast, I send you an array of just raw bytes. It's very hard to do anything with that. So what you really want to do is to use defined data formats, which allow you to basically do post-processing really easily, because there's metadata in there, which allows a standard metadata, which allows standard file processing tools to read that data, maybe visualize it, maybe analyze it, whatever. And so, nowadays you shouldn't really be writing your own files with their own metadata. You should be writing in the standard format, and we've talked about HDF5 and NetCDF, which have a big ecosystem of tooling support around them. The problem is the guys who've written NetCDF or HDF5 aren't going to go away and re-engineer their entire code base to take advantage of ARCHER2's lost to file system. So they've done by far the most sensible thing. They said, well, we will do our I/O using MPI-IO, and so we will leverage off all the vendor work on making MPI-IO hopefully work really well, and so they're layered up. So the solution is, well, you define higher level formats which have metadata, so you can actually say, what is this file? It's a 4x5x7 array of doubles, as opposed to an array of 1,120 bytes. Okay. But for performance, we layer on top of MPI-IO. So many real applications use higher level formats. But as I said, to understand the performance, then understanding MPI-IO will enable you to get performance as well. Well, hopefully, at least understand qualitatively how it will perform with number of nodes, number of stripes, number of aggregators, and such like. So HDF5, and I know very little about HDF5, it's hierarchical data format, it's set to file formats designed to store and organize a large amount of data, as Wikipedia says. It is very sophisticated in terms of you can have a lot of structure inside, self-describing, hierarchical. But for my exercise, my bench IO just calls HDF5 for this data set. So the HDF5 file is only a few bytes bigger than the MPI-IO one, because it's just a bit of data at the start saying, by the way, this is the 512 by 512, 512 array of doubles. But at least it illustrates the point. And the way that HDF5 works, and you can see this in the code. This is Fortran because I've just cut and pasted straight from the code, but it is also there in the C interface, is that basically you describe the global data set. You say, this is my data set. Globally, how big is it? And then each process describes its local portions of the global set. And HDF5 calls this a hyperslab. So there is a way in HDF5 to say that I own a hyperslab, an n-dimensional subset of this n-dimensional array, and that is what I own. And so the file space encodes the global data encodes the sizes. This is just saying we're using Fortran. This gives where I start, and this gives how big it is. So this is basically saying how big the global data set is, how big my local data set is, and where it starts. And they're called file space, offset, and count. But that's okay. And basically, HDF5, as long as you call the active IO version, hyperslabs will emerge to create a global file, and this can use aggregation in the way that the MPI-IO library likes to do. So you have to basically use collective IO. I can't quite remember how I do that. Sometimes it's a separate function call, sometimes it's a setup call, but anyway, that's how HDF5 works. So HDF5 layers on top of MPI-IO. NetCDF. So correct me if I'm wrong, but my feeling is that HDF5 is very general, but NetCDF. Excuse me, there's somebody at the door. Apologies for this. I think I'll be 2 seconds. Sorry, that's my fault. I took the key out, but then I put it back in when I took the bins in. Sorry about that. The perils of teaching from home. NetCDF builds on top of HDF5, but it's so HDF5 allows you to define any data set you want of any type. NetCDF is specifically designed for applications that do array-oriented data, such as climate research and oceanography, in a standard data set. And it's a specific version of HDF5, but for these very standard, for very commonly used formats. And so the way that it works on ARCHER2, so yeah, I'll come back. The chunking is something I'd like to, that's interesting. I have heard of this before. Yes, okay, we'll come back to that. Parallel net CDF, you basically, trying to find my slide again, sorry. You have the same, you have various calls, but basically you can set up a file, and here you specify your subset by, this is the global sizes, the dimension IDs. This says you want to do a write all because it's collective. And this is the starts, and these are the counts. So again, you could open a file, you can specify how big it is, what my subset is, where my subset starts, and you can specify collective I/O by using this NF90 collective. And there'll be similar things for the C, well, probably simpler interfaces for the C library. So here, NetCDF layers on top of HDF5, which layers on top of MPIO. So you do expect there to be some overhead at each stage, but historically it's been relatively small, 5, 10, 20%. That we seem to be getting quite a lot of difference there. What is interesting now is something called ADIOS2. Now, ADIOS2 is a much more recent parallel I/O library, and it has its own formats as well. It has the same overall approach. Each process defines what portion of the global data it owns and calls them read and write routines, but it's much more configurable at runtime. So, for example, you configure ADIOS2 via a config.xml file, so that again you can do a lot of configuration at runtime and not have to recompile. It says here not yet part of BenchIO, but it is now. So I have installed it into BenchIO. Now, what ADIOS2 can do is it does what I said you shouldn't do, is that under the hood it writes multiple files. So it gets really fast I/O by just basically dumping the file from a node into it. It basically writes a file per node. So it doesn't have to do any data aggregation or whatever. It says, look, each node just writes its writes its data to file. However, there is associated metadata, so you don't see that. You don't, when you read it in, it will do any reorganization or communications required to get it to the right format. So it hopefully gets the best of both worlds. It looks like a single file, however, it is fast to write because it will actually write it in lots and lots of different bits. So this is again, these are the same thing. This is what ADIOS2 looks like. All the same things to do that. You basically have all the same parameters specified in a different way. So how is ADIOS2 different? MPIO, HDF5, NetCDF the output file is independent of the process count or decomposition, which is great, but it requires a lot of data movement. And we've seen that with multiple aggregators, we get these funny issues like locking, which we've not been able to get past. For this ADIOS2, at least for its native format called BP5, under the hood, it writes one file per aggregator. By default, it uses one aggregator per node as well. There's no data movement, no locking issues, but this is invisible to you because it has metadata that hides this optimization from you. And so basically, it does work quite well. And HDF5 isn't necessarily an I/O format. You can actually go peer-to-peer. So you could output ADIOS2. You could output ADIOS2 format and read it from a visualization program, and they can communicate directly. You can plumb things together. I've not done it, but colleagues have, without actually having to go through file. So it is very good, but so I said MPIO may seem a little low level. I don't actually teach MPIO syntax anymore. but I think it's useful as a sandpit to play around with things, because it's the fundamental building block of most parallel on most systems. ADIOS 2, no, but the other ones, yes. Higher level formats build on top of MPIO. So they benefit from the work of the vendors like HP and the Lustre developers. The common ones are HDF5 and NetCDF. You might also want to look at the new ADIOS 2 library, but I still think understanding MPIO performance is key to getting good performance for HDF5 and NetCDF. Now, I've seen there's been some questions here. So the chunking, so I was surprised about the overhead with HDF5. We do run BenchIO or a version of it regularly on ARCHER2 as a test of, and I could go and speak to the guys that run that to see what they've seen before and after. HDF5 data chunking, I answered a query on this. I thought that was kind of orthogonal to striping, that it was an either or. I might be wrong. I thought the chunking was, I know I've heard people saying chunking is very important, but I can't remember. It was a query a couple of years ago. So that so you're right. HDF5 chunking is very like striping, but I thought that you didn't need to do both. I'm slightly confused. I don't really understand how HDF5 works. So yes. So yes, if you, yes, so hyperslabbing is the way to the collective. I mean, if you look at we can look at the code, but I said I basically adapted the code from a colleague's from previous work done by a colleague of mine, and so I'm not really an expert on the source code, but let's just share. Where are we? We're here. Let's go to BenchIO. Okay, so we were there. So we're looking for HDF5 to F90. So what does it do? So it's a array. There's a lot of setup here. Yeah, so I use native doubles. And I use collective. So I do use native doubles, and I use collective IO. And then I close it. So I don't. So at what point would one specify chunking? I thought that was some sense of orthogonal. There are these three concepts here: there's hyperslab, chunking, and stripes. I don't quite understand how they all fit together. I don't know if anyone knows. They're conceptually different or different terminology for the same thing. I think people should be able to speak by unmuting. Yeah, so you can just chat, Mark. I think you should be able to. You may not be able to share without my permission, but you should be able to speak, I think. Can you unmute?
There is unmuted. Can you hear me now?
Yep, can hear you fine, yeah.
Okay, great. So what we've been doing is we've been using the mostly NetCDF actually rather than HDF, but I think it's just a call from NetCDF to HDF to do. So we set the chunking at a variable level and specify the size of the chunks. And that's, I think, how the variable is then segregated within the NetCDF file. We found that there's quite a performance benefit from setting chunk sizes compared to just having contiguous data in the NetCDF file, whether or not we use striping. But if we set
what about
size,
what about hyperslab? Are you doing hyperslab
functionality?
Sorry.
We get better performance again. So we've seen that the chunking in the HDF layer and the striping at the luster layer are complementary, like they both add performance.
But I don't understand. Sorry, I talked over you a bit there. How does that correspond to the hyperslab? What is the format of your data? Is it not amenable to doing a simple hyperslab, because it requires regular data to do hyperslabs, obviously?
I'm not sure. So the setting of the chunking is something we tend to do through the NetCDF API. So I'm not completely sure how the NetCDF API then talks into the HDF layer.
Yeah.
But the functionality, I think, is available in both, because NetCDF only provided chunking when they adopted HDF5. The old NetCDF formats don't do any chunking. So at the point where you're specifying the variable, then you can either specify that it's contiguous or specify a chunk size.
Yeah. So we have. I did have some. So yeah. So there. It's complicated because there are three concepts here already. There's the striping on at the very lowest level. And then there's ways of getting NetCDF to split the data up, and I've been doing it with hyperslab. There's this concept of chunking. I don't quite understand how they fit together. One is sort of explicit and one is more implicit, I think. I don't really. Yeah. Let's just see.
I'm not sure about the directly at the HDF layer, just because I've got a bit less experience, but I'll have a quick look through the NetCDF layer in the bench IO and see if there's something that I can understand enough to send you a message and say,
yeah, that would be interesting.
There's a hook here, because it might be an interesting thing to do a compare on.
I am disappointed that I mean, a couple of things have changed, and that we do seem to be getting poorer performance, and I will need to follow that up with the people that monitor this. And so I think chunking is complementary to hyperslabbing. So you could do one or the other. I mean, you could clearly do both, but I would have thought, okay. So I'll share something here. That was my naive. Something that's weird has gone on here. Oh, because it's. So I'm just.
This is actually quite useful.
So for some reason, sometimes, it's very annoying. Won't let me share certain windows. Sometimes it just doesn't let me. There we are. I've got it now. So it says this is my Google. So they're saying, okay, so yeah.
Split it to me.
Index or yeah. So I'm. So I suspect this is sort of in the same space as. So yes. So it sounds like you could have a version of Bench IO that didn't do the hyperslabbing but used chunking. That and I'm sort of kind of reading between the lines here, but yes, that would. It sounds like an automatic way of doing the hyperslab in some sense. You don't have to do it by hand. So that does sound interesting. Yeah. So yes, that we could definitely look at that. And it is. I don't know. The benchmark is written in Fortran. I do have a version which was written by one of my MSc students last year in C. So hopefully easier to work with if you're not a Fortran programmer. But although actually no, it's for Adios 2. Apologies, Adios 2. Adios 2 is harder in C than it was in Fortran because Adios 2 supports C++, and the Fortran interface that uses modern Fortran is relatively nice.
Most of the basic NetCDF interfacing we write in Fortran. Our large-scale implementation is a wrapper around NetCDF that's written in C++, and that uses the C interface. But for basic programs, the NetCDF Fortran interface is very functional. a lot of the simulation code just talk directly to the NetCDF library from Fortran. I'll have a look to see if I can find something fit around this bench.io NetCDF that would let it do a chunking, non-chunking strategy. See if I can make sense. If I find anything, I'll let you know.
Yeah. So Harriet's saying that. So it sounds like more chunking. Chunking sounds more like luster striping, because it's something you create, something that you that defines it file creation, like lust, like a luster stripe. It affects the. But yes, so I did have a discussion with something about NetCDF chunking a while back, and we played around with it, but I can't remember what. So that's definitely something. But you're right. Yes. So what Harriet says, definitely that does help explain it. Yes. So what they're saying is that they. Yes. So I think they're using. If you want to, the problem you have with the default mapping of data is that a physically contiguous block of the simulation is spread across a wide variety of is spread across a large section of the data of the file. But if you write it out in chunks and they use some space filling curve to traverse the thing, then chunks which are close together in physical space will be close together in the linear mapping on the file. So I can see they're sort of that they're related, but slightly different. Yeah, okay, I think that's maybe what they're doing. I can't get my head around how that interacts with luster stripes, though, I have to say. I mean, per chunk compression, I have to say I've never quite understood that. I mean, can you really compress unless you've got lots of zeros? Well, maybe if you have, I don't know, if you're doing a simulation with lots of land and sea and the depth of the sea is 0 over all the land, do you store that? I don't know. I'm just surprised that anyone could compress double precision floating point simulation data. I've never really understood how that works, unless you explicitly have lots of zeros in there, for example. So yes, the questions are O focus. What about I? I wrote them as O focus because my naive statement was that most programs do more. So this is totally untrue about AI. So AI is completely the opposite thing, but most scientific simulation codes, I thought, probably did more input than output. So for example, if you're doing a weather simulation or climate forecast, you read the data in, then you run and you write out, you write the data out multiple times. So you write more than you read. Or if you're doing something like a lot of sort of quantum chemistry calculations can be defined by a very small data set, what the molecules and then you so however, if you look at the stats, that is not really quite true. They're actually probably about 50-50 if you look at the global stats on ARCHER2. And of course, for AI, it's completely different. AI reads in vast amounts of data and then says it's a cat. So I mean, so that was the application I originally dealt with. The other problem with input is it's harder to. So again, the version that my MSc student developed had at least a development one which did input as well as output. The problem is it's quite hard. You have to then create the input file to read it in. And so basically what you want to do is you really want to run you have to do some output first. So you want to write the data and then read it back in again, but then it's cached locally. So you have to do various tricks to make sure you're not reading. So my original assumption with input wasn't as scientifically or practically important to use this as output. However, that is possibly not true anymore. But it is also easier to write an output benchmark than an input one. So that is, yes, input is I think for a lot of people important, and for the AI people, unfortunately they're reading. Well, yeah, I don't know how they do their input, I have to say, but yeah, so that was my rationale, but it may not be relevant anymore. because we looked at the overall input versus output, aggregate file system stats for the whole year, and they were roughly similar. They varied a lot by file system, which means they vary a lot by user group. So it is definitely true that different user communities do very different ratios of input to output. But for example, climate scientists, contrary to what I thought, were doing more input than output, I think. I think they may have a lot of very big static data sets or something, they don't actually write out but need to read in. I'm not an expert at all. And obviously got topography, which doesn't change, but I was surprised when we actually looked at the data, I have to say. So that's a good question, and maybe not a very satisfactory answer. But I'm definitely going to go back to my colleague Luca, who runs a version of this benchmark regularly, to see what it's been looking like recently, as to whether So for that, there are tools which, on an application level, if we, what am I looking for? So a very simple thing you can do is basically, if you want to just get a broad brush idea of what your balance of input to output is, for example, and some statistics to give you some idea of what's going on, you can use something called Darshan, which is here. So it's on the ARCHER2 website. Again, I have to wait 10 seconds for it to appear. There we are. So basically, the nice thing about Darshan is you just do module load Darshan, srun, and module remove Darshan, and it will tell you things like, okay, I don't have but you basically, it dumps lots of data, and then you analyze it later with Darshan util. But I think, at the it gives you, it gives you an idea of, it'll easily tell you how much I/O how much input you did, how many output you did, and that can be useful. Oh, so Eva, you say Eva, where are you? Are you at the Met Office? No, I don't know where you are. Yes, okay, fine, yeah, fine. So yeah, so so it is useful. Yeah, it does not play nicely with other profiling tools, because all of these things try and hijack function calls. They hijack function calls and replace them with other things. But okay. But Darshan is a very good way of saying, am I writing 10 times as much as I read, or the same? Am I writing a terabyte or a gigabyte? I mean, basically, that's yeah. So okay, in the meta. So you're using. I've got confused. Are you using NetCDF or do you use XIOS? I'm not really an expert, but on these things, but I got confused with the names. I know that, is it Nemo uses XIOS? Writes NetCDF. Okay, yeah. So Nemo is XIOS is a whole other. I'm not an expert, so I have colleagues who are. Luca, who I mentioned before. You with XIOS, you identify at runtime separate physical resources, CPUs, i.e., you run two programs. You run Nemo and you run XIOS, and they talk to each other at runtime. So you have to decide at launch time how many of your processes are going to be Nemo processes and how many are going to be XIOS. And that, you're working with Luca, fine. Okay. Yeah. So and that can be that's a challenge there. But it's very, so they try and solve the I/O problem by decoupling it, by saying we will have dedicated I/O resources which can do I/O asynchronously and overlapped with and it's implemented as a separate program, which has its own challenges. On some systems, you have to launch 2 programs at once and get them to talk to each other. But that does work. But I know it can be tricky. Yeah. Okay, so I don't really have a lot more to say. I hope you found that useful. Apologies. I have sort of reduced this course down from a bigger one. I think it still shows its legacy in a few places. The MPI talk is maybe a bit too detailed, and for me, it was interesting to see people get different results from what I expected. I apologize. I mean, I checked the result. I checked that the exercises ran and gave sensible answers in advance, but I hadn't spotted that there has been some. I believe there's been a change in qualitative performance since September. However, the software update was absolutely necessary, so otherwise we wouldn't have been able to run ARCHER2 because none of its software would have been supported. So although it's can't guarantee, maybe it's possible that IO performance has gone slightly. Maybe it hasn't. Maybe I'm misinterpreting it. But even if it has, it's better to have slightly slower IO performance than no machine at all. So okay. So I hope you enjoyed that and found it interesting. I will save. I made quite a few changes to the slides. I will save them and then upload them, the PDFs again, because I put a few extra bits in and fixed a few typos and such like. And so I'm going to, okay, that's me finished now. And yeah, if you have any other questions, feel free to email them in or email me directly and I'll see what I can do. It's a bit of a busy time for me over the next few weeks because we have our MSc students submitting their final end of semester courseworks tomorrow for me, which need to be marked by university edict at short time scale. So that's kind of my focus, but I'm happy to discuss things. But if you do have any issues about IO, feel free to email into the help desk and we can pick them up. Okay, thanks very much. So goodbye. I'll stop recording and